As a motivation of our definition for boundary integrals, let us consider the situation that is commonly used in complex analysis. So here, let us consider a closed and simple curve say C in R2. So closed means that, okay, so suppose I have this parametrization, and let us consider this direction. So let us consider the parameter t. So C is defined as the image of some continuous function phi. So it's a map from the closed interval AB to R squared. It is continuously differentiable. So this would be the image of phi, so T in AB. And phi of A is equal to phi of B. This is responsible for the closeness of the curve. Okay, so the starting and the end point is the same. And that phi of, let's say, T is not equal to phi of S if T is not equal to S. So let's say if T is strictly less than S. So it will not cross, the curve will not cross itself. So this is what we mean by a simple curve. And I recall that we have the following line, sometimes called contour integral. So the integral of some, let's say, some function f defined on the curve, assuming that it is continuous. Okay. So f is a function from C, let's say, to R. It's continuous. Then this can be written as Riemann integral of the composition of f and the parametrization, okay, of phi, or I should say C. So this is a parametrization of your curve T times the line element, which is in this case 1 plus the derivative 1 plus the norm, the derivative of your parametrization squared dt. So this is the way we compute, or we compute the line or contour integrals. Let's say in complex analysis. So you can say this can map C to R2. So our goal here is to have a generalization to Rn. Of course, n is greater or equal to 2. So let's start with the definition. So consider a pair UG with U a subset of Rn, which is open, and G is a map from, let's say, Rn minus 1 into R, and this is C1. By this, we say that G is continuously differentiable. Then this pair, U and G, an open set and a continuously differentiable map is called a parametrization of a non-empty open and bounded domain omega in Rn at the point, let's say, x on the boundary, say x naught on the boundary if, okay, so we can find, so there exists an orthonormal basis. Let's call that basis z to the j from 1 to n, of the Euclidean space Rn, a parameter h for the height, a parameter r for, let's say, the radius, and a what we call reference point y naught. But this y naught, let's say, has components y naught 1 up to y naught n minus 1. So this is in Rn minus 1, such that the point on the boundary is a linear combination of the orthonormal basis in the following way. So the coefficients of y naught are the coefficients of x naught. Okay, so we have here a missing coordinate. That is the last basis, Zn. The coefficient is taken with respect to the function g. So this makes sense because y naught is in Rn minus 1. So this is, say, A, the first property. So to visualize this, consider this domain omega, and the black region here is the boundary. So this is the situation where, of course, n is equal to 2. So consider this portion of your boundary colored in blue, and consider the center, okay, x naught of this curve that lies on the boundary. The parameter h there is this height, and the parameter r would be this length. And here you have, let's say, this orthonormal basis. Let's say this is z2, and this is z1. And this is or should be orthogonal vectors. And your reference point would be this point here. So this is y naught. So in this case, y naught is equal to, or I should say, if y naught has the components y naught 1, y naught 2, then x naught is the following linear combination. So y naught z1 plus g of y naught z2. And that would be this vector. Okay. So here you rotate, of course, your coordinate axis. So that's the first condition. The second condition is the following. B, let's say, you can write U as the set of points in Rn. Let's say the components are x1 to xn, such that the Euclidean norm of this linear combination. So here we're taking all components except the last, minus the reference point. This is less than R. And at the same time, for the last component, xn minus g of the first n components is less than h. Geometrically, this U is the shaded region here. So think of this pair UG. So U is some neighborhood, H neighborhood of your portion of this boundary, and G is the curve that determines this boundary or portion of the boundary. So again, U here is the shaded region. And in this case, we also have the following. Xn is equal to gx1, xn minus 1. So this should be corrected to xn minus 1. This is true if and only if the point x is on the boundary. The second case is that if this is less than xn, but less than, let's say, h plus the image under G of the first n components. Let's say this is true if and only if x is in omega. So here the end coordinate is above the graph, and yeah, above the graph, and below G plus H. So this lower portion here, you can think of this as G plus H, and here you can think of this as G minus H. Because here our orientation is with respect to this coordinate system. So this would be U intersection omega, and this would be U intersection omega complement. So the other portion would be, so if you subtract the image, that's the graph, by H, this must be valid if and only if x is not on the boundary. I should say x is not on the domain omega. Okay, so this is a parameterization with respect to some point x naught. Okay, so you continue this, and let's say let us replace x naught by, instead of starting with x naught, let's say start with x1. Suppose you have parameterizations on a finite set of points, okay, on the boundary, and here the corresponding open sets are u1, u2, u3, u4, and u5. And so suppose that the union of these open sets u sub 1 up to u sub 5 cover the boundary. If that is the case, we shall call the domain a C1 domain. So more precisely, so omega is said to be a C1 domain if we can find a collection of parameterizations UK, GK. So you can have different open sets and different maps G. Okay. Let's say M is the number of parameterizations. Of the boundary at the point x sub k. Okay. Wherein this boundary is covered by these open sets, as visualized or as drawn in this figure. Okay, so there's still a missing point. Okay, so if we take this set that is interior, okay, that is in the interior of omega, and call that u naught. So let us define u naught subset of omega be open, be such that if I take the union of this u sub k's, now including u naught, I get the closure of omega. Okay, so take note that here omega, the closure of omega, is equal to omega and the boundary. So u naught somehow covers the missing parts of the omega by taking the union of the open sets in the parameterization. Okay, so let us denote by let's say Rk positive, H sub k positive, Y naught k. So this is the reference point of the kth parameterization. This is of course in Rn minus 1. And you have say zkj j from 1 to n basis in Rn. So suppose that these are the data corresponding to your parametrization. So you can have different R. So think of R, or more precisely 2R, as the width, and H the heights. So this orthonormal basis can be obtained, let's say, after some rotation of the canonical basis in Rn. So here we have superscripts k denoting the number of parametrizations. Okay, so consider an open set U. This will be either of these sets here, and a positive epsilon. So we define the so-called epsilon neighborhood of the boundary view in omega as follows. So you take this and consider a uniform with epsilon. Then the shaded region is what we call the epsilon neighborhood of U in, or epsilon neighborhood of the boundary view in capital U. And we denote it by n sub epsilon delta U, partial U. So this part here is the boundary. Okay. So that would be the set of all points, say x in Rn, more precisely in U, such that the distance of x, so we have here an x on the boundary, is less than epsilon. Take note here that the distance of a point from a set is the infimum of all y on the boundary, the distance between x and y. So this is the smallest distance between the point and on the boundary. And this can be, of course, obtained by, let's say, an orthogonal projection. So in this case, this would be the corresponding y that would be closest to the boundary. Okay, so now with this, it can be shown that there exists a so-called partition of unity call this phi k, k from 0 up to m. Okay, m here is the number of patches. So here we have 5 patches. Subordinate to the open cover uk, k from 0 to n, of the closure. By partition of unity, we mean that, okay, phi sub k is infinitely differentiable the values of phi k is between 0 to 1 on uk. There exists an epsilon sub k positive such that phi sub k is 0 on this epsilon sub k neighborhood of the boundary of u sub k. Okay. So except on, let's say, so phi sub k is 0 on this neighborhood. And moreover, as the name suggests, taking the sum of these functions will be identically 1 on the closure. So we divided, let's say, the constant function 1 into k or into m plus 1 pieces. So these are the functions phi sub k. The values are between 0 to 1. They are non-negative. They are infinitely differentiable. And they vanish near the boundary of uk. So the construction of this will not be provided in this lecture, but to those who are interested, you can consult a book by Munkres. So the name of the book is Analysis on Manifolds. So here, in the language of differential geometry, we also say that this C1 domain as a C1 manifold. So accepting this, we can now define measurability and integrability for a function f defined on the boundary. So we will say that a function defined on the boundary to be measurable, respectively integrable, if, okay, the composition of f and psi k, and I will define what is psi k later, on this ball, so r sub k are the parameters, and y not k are also the parameters corresponding to the parametrizations. These are measurable, respectively integrable for all k from 1 to m, where size sub k is the map from the ball into Rn, defined as follows. So psi sub k of y is the following linear combination. So we have here yj. Of course, yj are the components of your vector y. So this up to n minus 1. And then with respect to the orthonormal basis, okay, then you take the image of y zkn. So to illustrate this ball here, so going back to our previous figure, this would be the ball centered at y naught with radius r. Okay, so you do this for every ball in the parametrizations. So this is well, a function now in Rn, and we can talk about measurability. In particular, measurability with respect to the Borel sigma algebra. So in the case where your function is integrable, then we define the boundary integral so the notation would be as follows. F ds, the integral of on the boundary f ds. So s here, think of it as a surface. Okay, that is in the case of 3D. Okay, but we adapt that for the general case. So what we do is we integrate over Rn minus 1. So here we cut off f using the partition of unity. So take note that if you sum this over k, you get basically 1. Then take the composition of this with respect to the map psi k defined above. Okay, times the square root of, so this is analogous and to the 2D case. So you take the gradient of gk times the n minus 1 Lebesgue measure. Here, by the way, the gradient is the transpose of your Jacobi matrix. So again, this is the partition of unity, or the components of the partition of unity. So this makes sense because for an integrable function defined on the boundary, this is integrable on Rn minus 1. An important remark here is that I would like to highlight this definition is independent on the chosen parametrization of your boundary and the partition of unity on the closure. And the proof is quite technical, and those who are interested may consult our course notes. So now that we know the definition of boundary integrals and how to calculate it, at least in principle, we now state the well-known Gauss divergence theorem, where we rewrite the integral of the divergence of a vector field in terms of a boundary integral. So let's start with the assumptions. So again, suppose that omega is a C1 domain as defined previously, and consider a vector field F, let's say with components F1 to Fn, defined on the closure of omega into Rn. And suppose that this is continuously differentiable. So in other words, the component functions or the coordinate functions F1 to Fn are continuously differentiable, real valued functions. So the divergence of F, of your vector field F, is the map, okay, from omega bar into R. So this is now a real valued function. It is defined as follows. So divergence of F is the formally and the dot product of your gradient operator and F. So this is the sum of the jth partial derivative of the jth component. Then the integral over the domain omega of the divergence of your vector field with respect to the Lebesgue measure is the boundary integral of the dot product of your vector field with nu, where nu is the unit normal vector at the boundary outward of omega, or outward to omega. So suppose this is a portion of your boundary, and you have let's say a point here S on the boundary. Since your domain is C1, so this portion is a graph of a C1 function, of course after some rotation. You have a well-defined tangent, and once you have a tangent, you have this normal nu of S. So this is orthogonal to the tangent space at S, and it has a norm 1. This can be represented in terms of the function g corresponding to the parametrization, but I will not give the precise formula here. But think of this normal vector as orthogonal to the tangent vector at the point S. So we will not give the proof of this theorem, but it is important to at least be familiarized with this integration formula. So converting the integral over the domain omega of the divergence of the vector field as a boundary integral of the dot product of the vector field with the normal to the boundary. So the Gauss divergence theorem can be utilized in the derivation of various models in continuum physics. For instance, these are the heat conduction, electromagnetism, wave phenomena, and fluid flows, among others. It can be also used to prove the Green's first identity, and the Green's first identity is as follows. So the integral of the product of the Laplacian of f times g, okay, here the Laplacian of f is the divergence of the gradient field, okay, and f is what continuously twice differentiable on omega bar, okay, the closure of omega. This is the same as the boundary integral of the normal component of the gradient. So your derivative in the direction of the unit normal. So this is a line integral, or I should say a boundary integral, minus the integral of the product of the gradients. This follows from the Gauss divergence theorem. And G here is continuously differentiable. YC2, here we took two derivatives. So we need derivatives up to the second order to be continuous. However, here we only have the gradient, so we only need a continuity of the derivatives of G. And you may think of this as some sort of an integration by parts formula. That this Green's identity, in fact, this is the first version, follows from the Gauss divergence theorem. You will prove this in the last exercise of the course. So to end this lecture, let me present to you one application of the Gauss divergence theorem, which is the Reynolds transport theorem. And this is utilized in, let's say, in a fluid flow where convection is taken into account. So to illustrate the Reynolds transport theorem, so consider a domain omega, and think of this as your reference domain. And this is transported after some time t. So let's say this is omega t. And think of the subscript as the time variable. And this is, let's say, the transported domain after some time s. And so t and s is in I, let's say. So this is, think of this as some sort of your time interval. So suppose I have a function f, let's say, that depends on time, space and time. So x here is the coordinates, okay? let's say we have to calculate the integral of f. So think of f, let's say for instance, as a physical quantity. Let's say mass, momentum, or can be energy, let's say. So suppose I want to take the this physical quantity, and these are in densities. Okay. So, therefore, the integral would be the total mass or total momentum or total energy or net energy on or in the domain omega t. So the transported domain. And we are interested in looking at the rate of change. Okay, so here our t, the parameter t, and again, as I said, you can think of this as time. This domain omega depends on the time, and this function f, your densities also depend on time. So here we are aiming to get some sort of a Leibniz rule. So differentiating an integral where the function or the integrand depends on the variable of differentiation as well as the domain. Okay, so let us state now the Reynolds theorem more precisely. So consider an open interval in R, denoted by I, and a subset omega in Rn, that is reference domain, be a C1 domain. Now, suppose that the collection omega t, so think of this as the transported reference domain with respect to the parameter t. Suppose that this is a collection of C1 domains in Rn, and there exists, let's say, an open set in Rn that contains these transported domains omega. So for all t in the open interval I. So in this, suppose that this is our open set O that contains all the transported domains. Now, let us consider a map phi. Let phi be a mapping on omega cross I into the open set. So this is what? The map that responsible in or describing the transformation from omega to omega t. So take note here that this missing argument here is the one in omega. And let us consider this map in such a way that it is a C1 diffeomorphism for all t in I. The determinant of the Jacobi matrix is positive, okay, and finally we can interchange here the Jacobi or the Jacobian is taken with respect to y. Next, we can interchange the differentiation, so with respect to time and with respect to the space for all pair yt in omega cross I. And finally, moreover, suppose that we have this function u ut from omega t to Rn given as follows. So ut of x, and sometimes we will denote this also as uxt is defined as follows. So d phi dt of phi x t inverse, okay, and this makes sense because this phi is C1 diffeomorphism comma t. And this one is continuously differentiable for all t in I. So with these assumptions, for any, or let's say given a continuously differentiable map F defined on the closure of the open set omega containing all the transported domain into R, we have, okay, so taking the rate of change of this integral over the domain omega t, and there must be a Cartesian product, okay, on the domain of F, so that this integral makes sense. So this is the problem that we are looking a while ago. To calculate the derivative of this integral, this is the same as, okay, the integral omega t. So first you take the derivative of the integrand with respect to t plus, okay, so the effect of this quote-unquote moving domain would be the sum. So this would be the divergence with respect to the spatial coordinate or spatial variable xt u xt. with respect to the Lebesgue measure. So you can think of this as some sort of convection. And we know how to convert, of course, the integral of the divergence. So here we apply the Gauss divergence theorem for the second integral. So this would be, first, let us rewrite the first, let us copy the first integral. And the second would be plus applying the Gauss divergence theorem. So here you have the boundary Fs. S is a point on the boundary as t dot mu of s ds. Again, nu here is the normal vector outward to omega t. So for instance, this nu here. So this is the Reynolds transport theorem. And this integral formula plays a fundamental role in deriving, as I said, models in continuum physics, wherein we are taking into account some convective forces. So for instance, in the derivation of the well-known or the famous Navier-Stokes equation for viscous, or even for, let's say, for viscous flows, this transport theorem, or this Reynolds transport theorem, is utilized. In particular, the Eulerian form, or that is the Navier-Stokes equation in Eulerian frame. Okay, so this Reynolds transport theorem, the proof is provided in the course notes. So I will not give the details of the proof, but here the crucial parts are some. So we need some sort of results in matrix analysis, where you take the derivative of the determinant of a matrix. So those who are interested, you can look at the proof in the course notes. And further references are also provided there. And that's it for this series of lectures. In the succeeding one, we now discuss the so-called Lebesgue spaces. So these are function spaces that built upon the Lebesgue integral. So see you on that lecture.